here's the question we're looking at. All right, so what do we got here? Radius, the planet, they give us the mass of this planet and the radius of the planet. It orbits a star, gives us the mean radius of orbit here, of the orbital trajectory. A moon in circular orbit about the planet has a mass of the smaller mass, and it gives us its smaller radius. The distance between the center of the planet and the center of the moon is this distance right here. Okay, here's the orbital radius of the planet about the star. Okay, so it wants the magnitude of the acceleration due to gravity on the surface of the planet due to the moon. Okay, does that make sense? So we've got, if we want to draw a little picture of that, then we've got here's the planet. Here's the moon. And if we're taking a point right there on the planet, and we want to know what's the acceleration due to gravity caused by the moon. Okay? So this really, I mean, it's not a big deal. This is going to be the universal law of gravitation, but you just have to be careful about choosing the correct masses and distances, right? So we just have to fill in the blanks. We know that the force due to gravity equals m times the acceleration due to gravity, right? Which is g little m big M divided by r squared. So if we're just trying to find the acceleration, we could cancel the mass of the object for which we're measuring the acceleration, right? So if we're measuring the acceleration due to gravity on the surface of the Earth due to the moon, we can cancel out the mass of the Earth, and all we're really interested in is the mass of the moon, right? Okay. So if we plug in this stuff, then what are we going to get? So we're going to get G times the mass of the moon, which is right there, right? Divided by, what's the distance going to be?
It's just going to be the orbital radius minus the mean radius of the planet.
The orbital radius, what do you mean by orbital
Or
radius?
the distance between the centers.
Okay, so the distance between the centers of mass
And
of
then
the
that's going
Earth
to
and the
be
moon.
subtracted by the radius of the Earth.
Okay,
the
good.
planet.
Minus, then we're going to subtract back away the radius of the planet, right? Does that make sense? So then we've got the quantity on the bottom that's being squared is going to be 4.204 E8 minus radius of the planet's right there. 4.059 E6. Okay, so let's just throw all that stuff in our calculator, see what we get. Oops. So 6.67 E negative 11 times So there's the numerator, right? Now let's calculate the denominator. So denominator, we've got 4.204 E8 minus 4.059 E6 all squared. Okay, so we'll just take the top divided by the bottom, and we get something pretty small. Now, how many sig figs are we keeping here?
3.
Was it 3? Yeah, well, I guess. Was it 3?
Yeah, not the 4.48 E21.
Oh, there we go. Yeah, okay. So if we keep 3 sig figs, the answer to part A we get should be 1.72 e to the negative 6. And what should the units be?
MRS squared.
Yeah, meters per second squared. Good. Okay? Good. What about part 2? So part 2 is going to be very similar, right? Only difference in part 2 is, now this is, what do you think it's going to be, greater or less, the contribution due to the star?
Less.
I would guess less because it's so far away. So let's see here. We're finding the acceleration of gravity on the surface of the planet due to the star. So now, same situation as before, but now this is the star. Whoops, that's going to be the star instead of the moon, right? So really, all we got to do, same calculation. Mass of the star is very big.
It's not given.
Oh, it's not given.
Yeah.
Oh.
That's why there's a problem.
Yeah, it is a problem. Yeah, okay. Yeah, you can't do this without the mass of the star. Okay. No wonder there's a problem. Huh. Okay. I'll add the mass of the star. It's going to be. Why is it not popping up? I wonder.
6.
Okay, what about one like that? What's providing this centripetal acceleration this time?
The tension is.
Tension, sure. So all we need, think about this one. You could even probably do this without drawing a free body diagram. In a gravity-free environment, there's only one force acting, and that's tension, right? So what does the tension need to be? MA, right? And what's A? Well, A is going to be, in this case, we're given period, and we're given radius, right? And so do you remember what the formula for centripetal acceleration is in terms of T and R?
2 pi over r.
Okay, that's V, isn't it? 2 pi r. So there's one way we could do this. We could say that the orbital speed, in this case, is just going to be circumference divided by period. The distance around the circle divided by the time it takes to go once around the circle. And then we could use V squared over R. That would be fine. We did have a relationship in terms of R and T. We haven't used this as much. Do you remember what it is? Centripetal acceleration.
V squared over r. And
Well, we can do that. So let's do that. So we get V squared over R. So there's my V. So we get 2 pi R over T squared over R, right? So then we could just expand, we could just square this whole thing out, and that's going to give us 4 pi squared R squared over T squared, and then times 1 over R, right? So we could cancel one of those. So we get 4 pi squared over t squared. 4 pi squared r over t squared.
Where does the mass come in? Doesn't it?
Okay, so the mass, right, so then that's the acceleration, right? But we know that the centripetal force equals m times centripetal acceleration, right? So we know what the mass of the steel ball is. We have to convert that to kilograms, right? But we could multiply whatever acceleration we calculate from that radius and that period times the mass, and that's going to give us the necessary centripetal force. If the mass increases, what does that tell us about the tension? What's going to happen to the tension if instead of, like if we have a small marble and
If the mass increases and nothing else changes, the tension will increase.
tension's going to have to increase too, isn't it? Right, good. Okay, make sense? Okay.
What were you trying to do with the AC at the top there at first?
Well, so if when all the dust settles here, what do we get? Centripetal acceleration equals 4 pi squared r over t squared. Okay. And really we could, I'll put these on the, okay, this would be a little helpful. I wasn't necessarily going to do this, but I will. So we could come up with a couple equations if we want to. Right, so let's derive these once as a class, and then I'll put them on the formula sheet for you for the test. Okay? So what if we did something like this? What if we wanted to know so if we wanted to know the speed of an object in circular orbit, right? So if an object is in circular orbit, we already know that centripetal acceleration equals g m over r squared, right? Does that make sense? So if we have an object orbiting a planet, this is going to be the mass of the planet, and that's the radius, distance between the object and the center of the planet, right? Well, what's centripetal acceleration? That's v squared over r, right? So we could then, if we wanted to solve for v, that's no big deal here, right? We could multiply each side by r and take a square root, and then I could cancel, right? Cancel one of those. And I'd end up with v squared equals gm over r. And so if I square root both sides, we do come up with a little formula, right? And we do this enough that, I'd be okay with you using that formula if you want to, right? So if you have a satellite orbiting something massive, that's always going to be the way you could easily calculate the orbital speed at a given radius, okay? I'll put that one on the cheat sheet for you. Okay, how about, what if we wanted to know the period? Okay, if we wanted to know the period, what could we do? Yeah, we could just make that 2 pi r over t, right? Equals this. And if I want to solve for t, what would I do? I could flip both sides. So t over 2 pi r equals the square root of r over gm, right? Just to make things easier here, how about if we square both sides too? We wouldn't have to do this, but just to get rid of the radical. That's going to give us t squared over 4 pi r squared, agreed? Equals r,
Pi squared.
pi squared, you're right, pi squared, r squared over r equals r over gm, right? So if I multiply each side through by 4 pi squared r squared, cancel those guys, right? Square root both sides. And what do we get? We get
4 pi squared r cubed divided by gm.
okay. And we could be a little bit tricky with that. What's the square root of 4?
2.
So I could pull that 2 out front. What's the square root of pi squared?
Pi. Oh, that's the period.
See how that works?
Oh,
Okay, and so there's another one we can come up with. I'll put that on the formula sheet. So the period associated with a satellite orbiting a planet or a star, doesn't matter what it is, something big, is going to be this.
Could you take out an R?
You could, yeah, but then you'd have one R out and one R in, so it's probably easier. Generally, this is the way that formula is written. When you write the formula, they just keep the R cubed inside. So you only have to deal with the R once.
What does it mean? Because when you take out the R, you get the circumference formula. So you're multiplying the circumference by the, if you were to take out the R.
Oh, true, yeah.
It'd be multiplied.
So, right, and so, I mean, yeah, it's interesting that it is that way. You're multiplying the circumference by the square root of R over GM by some factor. So it is interesting that the circumference does pop out, but it ends up not being that useful because we'd rather not have to introduce two things to think about, a circumference measurement and a radius. We'd rather just deal with either the circumference or the radius, okay? So we do get these two pretty convenient formulas, right? And just remember that when we talk about a big M, that's the mass of the gravitational center, we'll call it. Whether it's a communications satellite orbiting the Earth, or it's a planet orbiting a star, or it's a star orbiting the center of a galaxy, it doesn't matter, right? This is going to be the formula that's going to apply. But capital M is just the big mass. The other one is negligible. Okay? So I'll throw those two on there for you. But you've already done all this stuff. I mean, you've done problems without those. It's not like you couldn't get by without them. But they're convenient. Okay. All right, I'll let you work. We'll test tomorrow, and then we'll get back to work and energy stuff on Wednesday. I thought